Swayam Prabha. Digital India. Educated India.
We will discuss systems with constraints a little further, and in this lecture I am going to introduce non-holonomic constraints. Till the last lecture we were discussing constraints which were holonomic, which were in terms of the coordinates, which are called holonomic constraints by the way, and we had looked at derivation of the equation of motion using the method of Lagrange multipliers, and we also interpreted the Lagrange multipliers later on to determine the constraint forces. In this lecture I am going to introduce non-holonomic constraints. The process remains roughly the same, and we are going to look at an example. What are non-holonomic constraints? Just to recapitulate, they are non-integrable constraints, constraints which come with derivatives of the coordinates and which we cannot integrate out. We cannot integrate, we cannot write a non-holonomic constraint in terms of only the coordinates, then it becomes a holonomic constraint actually. The constraints which cannot be integrated, which come in terms of derivatives, they involve the derivatives of the coordinates, they are non-holonomic constraints. Non-integrable constraints are non-holonomic constraints. So, non-integrable in the sense that they involve the rate of change of coordinates, and that cannot be integrated out. We will consider systems which are where the non-holonomic constraints are linear in the generalized velocities. So, they are linear in terms of the coordinate time rates. Now, here is a general example, the constraint vector C. So, I have considered m minus n non-holonomic constraints. We have therefore a vector of these non-holonomic constraints. Of course, you can have mixture of holonomic and non-holonomic, but I am considering only non-holonomic constraints, m minus n of them. They can be written like this matrix m minus n cross m. Remember, m is the number of these physical coordinates, r is the physical coordinate vector. This is the physical coordinate vector rate, and you will notice that the constraint is linear in terms of the rate of change of the physical coordinate. It is linear in terms of the rate of change of the physical coordinate vector, and these m minus n constraints can in general therefore be written as a matrix which has a size of m minus n cross m dot the rate of the physical coordinates, rate of time rate of the physical coordinates, m of them are there, plus another vector b. Now, this a, b, they can involve the coordinate, the time, etc., but they will not involve derivative of the coordinate themselves. That dot product that you find in the first equation can be written as a summation, and that matrix A can be written with indices A, j, I, and this is the jth constraint, and j goes from 1 to m minus n. And here therefore, I can write, because this is 0, all these constraints must vanish, therefore, I can write this in terms of d r I. I have multiplied by dt throughout and written like this. How do I write the variational form of the constraint now? Imagine for a moment that we had a general function f r t. What do I get when I do d of f? I get d del f del r I d r I. This must be summed over I runs from 1 to m, and plus del f del t dt. This is total derivative, and this is different from the delta operator. Remember, this is the total derivative operator, therefore, it derivates the time also. This is what we are going to obtain. Imagine that somehow, I mean this is just stretching a little bit your imagination, that these are actually these terms, and this d r I is sitting like this, and you have del f del t is this b j, f can be a vector function of course, and then you will have this b j times d t, though this a j I cannot be written as partial derivatives. Why? Because our constraint is actually non integrable, therefore, we cannot actually write, but just stretch your little imagination and think about it, that if I had the constraints in this form, then what would I have done? I would have, if my constraint had been this, then my variation of the constraint was delta c, which looks like del f del r I delta r I summation etcetera, and there was no delta t, because this variational operator delta does not derivate time. If I think about it, it is this one, this expression is like saying that this and that is it. So, this is delta f. In other words, my variation, my virtual displacement, these are virtual displacements, remember. These are virtual, delta r I are the virtual displacements with time frozen. These virtual displacements are being made in the direction of the, you can think about velocity vector, in the direction of the variation of the coordinates and in the direction of velocity of the coordinates. And now, you think that these a j I as it is, you do not think in terms of del f del r I something, because a j I are not some partial derivatives, they cannot be, otherwise the constraint would have become integrable. Keep a j I as it is and just convert this d r I as delta r I and drop this term dt, because the delta operator does not derivate time. In other words, we are taking variation in the direction of the coordinate rates, so that our non-holonomic constraints are respected. We will take virtual displacements which respect the non-holonomic constraint, which respect the velocity constraint. After all, non-holonomic constraints represent velocity constraints, they are constraints on the velocity. You cannot have arbitrary velocities in a non-holonomic system. This velocity must be such that it satisfies this condition, velocities must be such that it satisfies this condition, and our variations do it, our variations do satisfy that constraint, that virtual displacement does satisfy the velocity constraint. We have dropped this term because that came as if that came from that time derivative. which our virtual displacement do not have. Therefore, our delta Cj are of this form, and remember, because of this non-holonomic constraint from where we have found this, this is something like, this is a quantity by itself. It is not a variation of a scalar quantity called C. It is not to be supposed as a variation of a scalar quantity C, because these are non-integrable and they are not like partial derivatives, as we just now saw. Now, Hamilton's principle, this is the variational principle, delta L, the variation of the action must be 0. This is where we come up to, and here we do not have independence of choice of delta r, the variations. We do not have independence of choice. Why? Because there is constraint on the velocity. We cannot give arbitrary variational displacements. I must give variational displacements that respect our non-holonomic constraint. This is what our plan was. So, that is what we are going to do. This I have just written out this dot product as a summation. I have written out the dot product as a summation, you can check this, and I have written out individual coordinates r1, r2, etc. Remember that this delta r1, delta r2 up to delta rm, they cannot be chosen independently, because variations cannot be given independently due to the non-holonomic constraints. We have this variational statement subject to, now these are our constraints, and the variations in our physical coordinates, which are delta r1, delta r2, delta rm, these must satisfy all these conditions. What do? We just use the method of Lagrange multiplier and push these constraints into our variational statement and get a combined statement. We use m minus n Lagrange multipliers. Why? Because we have m minus n constraints. Multiply each constraint by 1 lambda and sum over all these constraints, which I have written here. And then you add it to the variational statement, and we have the combined statement from where we will derive our equations of motion. And now we know what is the interpretation of this. We have this quantity which is energy or work. Therefore, this also must have that same dimensions. Now, let us proceed. What we are going to do is, we are going to combine these terms and pull out the coordinate, ith coordinate I have pulled out and written this as a summation. I have pulled out the ith coordinate, variation of the ith coordinate or the virtual displacement in the ith coordinate direction, and the corresponding coefficient is sitting in this bracket, and I have a sum over all these physical coordinates. Now, this I mean, introducing the constraint using Lagrange multiplier was done to take care of the fact that we do not have this freedom of arbitrary variations of the physical coordinates. But now we have these Lagrange multipliers to play with. What we are going to do is, we are going to drop out, make these coefficients of those coordinates or their variations of these coordinates, we will make those things 0 which we do not have freedom of choice. Rest of it we have freedom, and we will individually make them as 0. This was our argument, which we have discussed before also. We choose lambda j's from j1 to m minus n, such that let us say from I equal to 1 to m minus n, because I have m minus n choices of lambda, Therefore, in this summation from 1 I equal to 1 to m minus n, those coefficients I put them to 0 by special choice of lambda, and I suppose we can do that. That depends on invertibility of a certain matrix, and we will assume all these good features of our constraints, that they are linearly independent, etc. Then this can be determined. I can find out lambdas, so that the first m minus n equations, just the coefficients drop out. The rest I can choose delta ri's independently for the rest. Then the integral 1 vanishes for arbitrary delta ri, where now I starts from m minus n plus 1 and goes up to the total number of physical coordinates, which is m. Now, these can be chosen arbitrarily, and therefore, their coefficients must be 0 for the integral to vanish. Some of the bracketed quantities I have made 0 by special choice of lambda, the rest must be 0 individually, because the other delta ri's must or can be chosen independently. From ri, delta ri, I going from m minus n plus 1 to m, they can be chosen arbitrarily, and therefore, their coefficients must vanish. But remember, the choice of lambda was made here, therefore, here lambda is known. But we really do not have to solve for lambda this way, and this we had discussed again. We have these two sets which must vanish. The first set goes from I equal to 1 to m minus n, the second set goes from m minus n plus 1 to m. That means, we are actually putting to 0 all the bracketed coefficients of delta ri's, but the argument why we can put this is not straightforward, that we have discussed how we are doing it, and not just because delta ri's are independent, but we have found lambdas for those delta ri's which we cannot choose independently. For them, our coefficients we have vanished by special choice of lambda. But then you see that we do not have to find out lambda that way, we keep the lambda in our equations. These are our equations of motion, and later on we have learned we have already learned this actually, how to eliminate lambda, solve for lambda, etc. That we are going to use. Now, we have m equations of motion, but there are 2m minus n unknowns. Why 2m minus n unknowns? We have m coordinates, and we have for individual coordinate we have one equation. Therefore, there are of course m equations. How many unknowns? We had m coordinates plus m minus n Lagrange multipliers. We had m coordinates and m minus n Lagrange multipliers, which have to be found, lambda i's, ri's and lambda i's. Therefore, we have 2m minus n unknowns, but then these are only equations of motion, we have not written the constraints as yet. We also have the constraint. Now, the constraints are in full form, you can check that the constraints are in full form, we have that b added to it. These are the complete constraints. Therefore, we have m equations and m minus n constraints, therefore, we have 2m minus n equations in 2m minus n unknowns, but then realize that we have second order differential equations from the Lagrange's equation. We have second order differential equations, ordinary differential equations, which are m in number, and we have first order ordinary differential equations from the constraints. Now, this set of equations and constraints they are a little inconvenient because this lambda comes as an additional thing, how to solve for lambda, but we have our steps and we have discussed these steps before. So, we have 2 m minus n equations and 2 m minus n unknowns. We are good at our thing is well set, it is well defined, but then we want to get a little convenient form. Therefore, we have discussed these steps: determination and elimination of Lagrange multipliers, you time derivate. Now, you see in the holonomic constraint case, we had to time derivate 2 times to get to acceleration, double derivative of the coordinates with time. But here we have non-holonomic constraints which already involve the first derivative with respect to time of the coordinates. What we have to do is we have to only derivate once, and this I have written as a general expression. Nothing to worry about the very strange form or very complex form. I have written it out in the summation form. When I take a time derivative, when I take the time derivative of the constraint, of course, r I dot will get time derivated once, and this a j I, which is the matrix, this also gets time derivated, and the derivative of the coordinate, the corresponding derivative of the coordinate, which I have written like this, and time derivative of b j's, which I can write like this. Now, this occurs for each j, for each constraint this happens. Do not worry about this complex form. What is d j I k? It is nothing but the derivative of a j I with the coordinate k. So, del a j I del x del r k. This is this. Okay. Then we move forward. Now, eliminate the accelerations using the equations of motion, which we already have, the second order ordinary differential equations, which are our equations of motion, Lagrange's equation of motion. Eliminate the accelerations. Now, this step can be quite complex, but theoretically we can always do it, and then you can solve for the Lagrange multipliers. They are in terms of lower order derivatives, 0th order or 1st order, because 2nd order has been eliminated. Using this Lagrange multiplier, you substitute back in the equations of motion. Then you have eliminated the Lagrange multipliers, which will now be in terms of the coordinates and their first time derivative only, no second time derivative. Now, that will give us self standing equations of motion, m equations in m unknowns. We can integrate that, but we have to set the initial conditions carefully. Setting up the initial conditions, we use, because the initial conditions must satisfy the constraints, remember the initial conditions must satisfy the constraints, because there are m coordinates and we have now self standing m second order ordinary differential equations. Therefore, we will require 2 m initial conditions. Let us say these are the 2 m initial conditions, the coordinate values at 0 time t equal to 0 and coordinate derivatives, the first derivative at time t equal to 0. So, 2 m conditions, but they are not all independent because the constraint has to be satisfied. You may also have holonomic constraints, then you have additional conditions. Here I am only discussing the non-holonomic constraints. We have the non-holonomic constraints m minus n, therefore, these many conditions must be satisfied. I have opened it up for you and written it using these initial conditions that you can see here. These are the positional initial conditions r 0, and we have these velocity conditions, velocity initial conditions. Now, all these things must satisfy this constraint, that this must be equal to 0 for all the constraints. Therefore, we have these 2 m initial conditions, but not all independent. How many independent? Minus the number of constraints, so 2 m minus n, that gives us m plus n independent initial conditions. Now, let us look at this example, which we have discussed actually before, the dynamics of a rolling coin. Coordinates are x, c, y, c, which are the contact point coordinates of the coin with the ground. I have shown it on the figure, x, c, y, c are the ground contact points. So, those two coordinates and the orientational coordinates psi and phi. Psi is the angle that the tangent to the path at this instant makes with the x axis. Psi is the angle that the tangent to the path, this is the tangent to the path that makes with the x axis. So, this angle is psi. Phi is this orientational coordinate, which is the tilt of the coin with the vertical, which is the z axis, and the spin theta, which I have shown. These are our coordinates. Of course, this ground contact point, I mean this always in ground contact, that constraint was holonomic constraint, that has been taken care of, but in order to find out zg, which we will require very soon, we write it as r cosine phi, which you can check, that is the z coordinate of the center of mass, and we have these non-holonomic constraints, x c dot minus r theta dot cos psi equal to 0 and y c dot minus r theta dot sin psi equal to 0, and these cannot be integrated, they cannot be integrated. Now, to use the Lagrange's formulation, Lagrangian mechanics, we have to write down the kinetic energy, potential energy of the coin. And we know that in order to write down the kinetic energy, we need the velocity of the center of mass and the rotation about the center of mass. The center of mass position, we start with the position vector of the center of mass in the x y z frame, which is shown, which is the fixed frame. And these relations we had derived in an earlier lecture, x g, y g, z g, which are the positional coordinates of the point g, which is the center of mass of the coin. I can derivate that to find out the velocity, which I have done here. This straightforward derivative, there is nothing else involved, because why? Because this x y z is a fixed coordinate system, it is a non-rotating coordinate system, there is no frame derivative. Therefore, only these coordinates get derivated. Total translational kinetic energy is half m x g dot square plus y g dot square plus z g dot square as usual, and this is what comes out of it, a little complex, which you can always do. We have to just do the algebra, otherwise it is straightforward. So, this is the translational kinetic energy. Next we go to the rotational kinetic energy, and here we have discussed these things, we will just go through it quickly. It is very easy to write down the angular velocity in the x prime, y prime, z prime frame. And why do we use this x prime, y prime, z prime frame? The reason is the moment of inertia tensor in this frame is constant, even though the coin is rotating with respect to this frame. This frame is not a body fixed frame, but this frame is somehow very interestingly chosen, so that even if the coin rotates, even if the coin spins, its moment of inertia tensor in this frame remains invariant, because the coin is an axisymmetric body. The coin is an axisymmetric body. Using that fact, we have set our coordinate system such that the moment of inertia tensor of the coin in this frame is constant. You see, the z prime axis and x prime axis have been chosen very carefully, so that the coin is always in the x prime z prime frame. This x prime z prime frame has been shown in the figure. The coin always lies in the x prime z prime frame, and this y prime, which is not marked but shown, the y prime coordinate direction is perpendicular to the face of the coin, and the coin being axisymmetric, whatever happens to the coin now, the coin is always in the x prime z prime plane, and therefore, its moment of inertia tensor is constant. Therefore, we will find out the rotational kinetic energy in this frame using the moment of inertia tensor, which is constant, and hence we write down the angular velocity of the coin in this frame omega prime. This we have written before. The moment of inertia tensor, very easy to write for a disk like object. Rotational kinetic energy is nothing but half of omega prime dot I g omega prime. Now, because rotational kinetic energy or kinetic energy is a scalar quantity, whichever coordinate system you use to compute this will remain invariant. Just like the magnitude of a vector, whatever frame you use to represent it in, the magnitude of a vector remains invariant. So, similarly, the kinetic energy of rotation, even though we have used the x prime, y prime, z prime frame, the kinetic energy expression will remain the same. So, we have used this frame for convenience, and if you open up, then it gives us a very complex expression, but this is slightly simpler than the translational kinetic energy. Therefore, we have the translational kinetic energy and rotational kinetic energy. I am not doing the detailed steps, I leave that to you to work out. These are our two kinetic energy expressions. The potential energy can be written very easily. This is the we are taking x y plane as our datum, and with respect to that, this is our potential energy expression m g z, really m g z g, m g z g. This is nothing but m g z of the center of mass. Okay, we proceed further. So, Lagrangian is ready, the kinetic energy minus the potential energy. In addition, we have these constraints, the non-holonomic constraints. This is our complete expression of the Lagrangian and the constraint. The variational problem with the constraint introduced using Lagrange multipliers. We have two constraints. They are, therefore, we have two Lagrange multipliers to push them into the variational statement, and this is our complete statement, from where we can derive the equations of motion, but they are extremely complex, as you can imagine. We will not try to derive these equations of motion. I leave that to you, to your interest. You can use a symbolic toolbox or a software to derive the equations as well, because these are complex equations, highly nonlinear and coupled. You have to be careful while deriving the equations of motion. I will just look at the interpretation of these Lagrange multipliers. This is our statement. Now, whatever term I have introduced using the Lagrange multiplier, that must be the virtual work done by the constraint forces. Now, this is what I have written out, and lambdas we have interpreted in terms of they may not be directly the forces, but they involve or they give us, they are proportional to the constraint forces. Let us look at this point a little further. What are our constraint forces? This is the free body diagram of the coin or the disc. Notice we have these constraint forces. One is tangential to the path. This is our tangent to the path. This, therefore, is the tangential force at the point of contact. This is normal to the path. This is the force which is normal to the path. I have chosen to decompose the constraint forces, in plane constraint forces, as tangent to the path and normal to the path, Ft and Fn vectors. And I have this normal reaction from the ground as usual, and the weight of the coin acting at the center of mass. So, these are our constraint forces, and these constraint forces therefore must be Ft plus Fn vectors dot the variation in the coordinate xc and yc, the variation in the coordinate xc and yc, that written as a vector. Now, remember, you have a variation vector. I can give an arbitrary virtual displacement delta xc delta yc is a vector that I have written in terms of I cap and j cap, and that dot product with the in plane forces that will generate work. Also, if I change the spin, if I give additional spin, being at the same contact point, if I give an additional spin, I will have work because of the tangential force. But delta theta, the virtual displacement in the theta direction, is an angular displacement. Therefore, I must have a moment to have the correct dimension of work, and the moment must be radius of the coin times the tangential force. The normal force will not do any work, right, neither the normal reaction from the ground. Therefore, this is our work done from the variation in the spin of the coin. You have to account for everything, all virtual work components. Now, this Ft vector, the force which is tangential to the path at this instant, can be written using the angle psi, which you can see here. Using this angle psi, I can write, or I can express in the x y coordinates like this, the magnitude times the unit vector in the tangential direction. Similarly, I can represent the normal force Fn, normal to the path Fn, as magnitude times the unit vector in the normal direction, normal to the path direction. And using all these expressions, I can now write down my grand expression of virtual work done by the constraint forces. I have contributions from variation in delta xc, delta yc, delta theta. There is no contribution due to variation in delta psi or variation in delta phi. Why? Because if I change psi, being at this point, if I change psi, no work is done. The contact point remains where it is. If I change phi, the inclination angle, no work is done, because the contact point remains at that location itself. There is no slip generated, therefore, no work done. No work done by the constraints, of course, no work done by the constraints. And this I should be able to write as lambda 1 delta xc plus lambda 2 delta yc, and this expression delta theta. Now, how do I get that? I get from our virtual work done by the constraint forces. You see, this is lambda 1 delta xc, lambda 2 delta yc. I have generated these two, and now for delta theta I have contributions from both these terms, and that is what I get. That is the expression of work done, virtual work done by the constraint forces, as we get from the variational statement with the constraints. I can now compare, so that I can relate these lambdas with Ft, Fn, etc. I can relate, I can compare these two expressions. Remember, these two expressions have come from two sources. This has come from our free body diagram, the virtual work done from the free body diagram, which means we have used the physical forces, and this has come from our variational statement. Therefore, I can compare and write down these two expressions. Lambda 1 must be this, lambda 2 must be this, and r times f t must be this. Therefore, I must have this lambda 1 as this expression, lambda 2 expression, all these things I have. I can solve for f t and f n. I can now solve for f t. These are two simultaneous equations in f t and f n. I can solve in terms of lambda 1 and lambda 2. Therefore, once I solve the problem and find out lambda 1 and lambda 2 by the procedure we have discussed so many times, we can find out, finally we can find out what are f t and f n. And you see this is consistent, this is f t and same here. So, we have a consistency. Let us look back a little bit again, the Lagrangian and the constraints. Can we do something about it? Not involving the Lagrange multipliers, can we do something? We can. If you notice carefully, the Lagrangian has only the time derivatives of x c and y c everywhere. There is no x c or y c appearing there, everywhere we have x c dot or y c dot, and we have x c dot and y c dot in terms of theta dot psi, in terms of the angular coordinates, the orientation and spin coordinates. Therefore, I can get to a reduced Lagrangian using these constraints to eliminate x c dot and y c dot, to get the Lagrangian solely in terms of the orientational and the spin coordinates psi, theta and phi. This is our reduced Lagrangian. Therefore, I can derive the equations of motion, I can take phi, theta, psi as independent coordinates and derive the equations of motion, but in this approach we cannot find the constraint forces. By this we cannot find the constraint forces have gone in. But do we care? Well, it depends. I mean, if I am just interested in the dynamics of the coin, of a rolling coin, I am not really bothered right now about the constraint forces, whether slipping is taking place or skidding. I consider that okay, to be safe, I assume that there is enough friction so that it does not slip. Under those assumptions, we can derive the equations of motion and do something interesting. These are our equations of motion corresponding to the spin coordinate theta, the tilt coordinate phi and the angular, the orientational coordinate psi. Along with that, since I have to find out x c and y c, I must also integrate these equations which come from the constraints. These are of course first order differential equations, first order ordinary differential equations. The first three equations are self standing, as you can note. These are only in terms of theta, phi, psi, they are self standing, you can integrate them, and along with that you also integrate these two additional equations to find out where the coin goes, and that can be done. And here I have done this thing, I have made a simulation out of this. The first example that I am showing here, here I have the initial condition at time t equal to 0, phi is 0.1 radian, there is a tilt, and theta dot the spin rate, I give a spin to the coin and I consider that it is rolling without slipping. That initial spin rate is 9 radian per second, and I allow the simulation to run, and this is what I obtain. Notice carefully that this ring has been given a little lower spin rate, so that it appears it is on the verge of falling down, like this here, but it somehow makes up because it gains angular momentum and then it makes up. Notice one another thing, here is the trace of the XCYC. On the right I show the trace of XCYC, and you will notice a constant drift. It started like this, but then it starts drifting like this, and you will notice the drift. It starts from here, and you will notice when it comes back to the origin of the coordinate system, there is slight shift from the y axis. This is our y axis, this is our x axis, this is the z axis, this is the y. There is no dissipation, no energy dissipation, therefore, this will keep moving, but this you cannot observe in reality, because there is always some dissipation, and after some time this ring will fall down or the coin will fall down. I have another simulation with a slightly higher spin rate, and now you will find that it is getting closer to a circle. The xy plot is getting closer to a circle, which means what? The spin rate that I have given and the tilt that I have given are not conducive to pure rolling with constant tilt. I can increase the spin rate a little more and maybe get to a very steady rolling of the coin without changing tilt. It will of course roll on a circle, then it will roll on a perfect circle, and here it has come to a circle, but if I increase the initial spin rate a little further, if I increase it a little further, maybe it will go to, for that tilt angle which is 0.1 radian. I have kept the tilt angle the same in both the simulations. For that tilt angle I need a little more spin to make a perfect circular track on xy plane. Let me summarize. We have looked at systems with non-holonomic constraints, used Lagrange multipliers, we have interpreted Lagrange multipliers, and we have discussed an example of the rolling coin. With that I will close this lecture.